Imagine standing beneath a bridge so high that the clouds seem to move beneath your feet, while hundreds of meters below, a river cuts through one of the most dangerous mountain landscapes on Earth. This is not a scene from a science fiction movie. It is the Chenab Rail Bridge, built deep inside the Himalayas in India, a massive steel structure rising approximately 359 meters above the Chenab River, making it one of the highest railway bridges in the world and the highest railway arch bridge ever constructed. But the incredible part isn't simply how high it is, it's where India decided to build it. The bridge stands in Jammu and Kashmir, surrounded by enormous mountains, unstable slopes, extreme weather, earthquakes and powerful winds, in a region where even reaching the construction site was a challenge. So how do you build a railway bridge in a place where nature itself seems determined to stop you? The story begins with a much bigger problem. For decades, connecting the Kashmir Valley with the rest of India's railway network had been one of the country's most ambitious infrastructure goals. The railway needed to cross some of the most difficult terrain in the Himalayas, where valleys could suddenly become hundreds of meters deep and mountains could rise almost vertically from the river below. A conventional bridge simply wasn't going to work. Engineers needed something enormous, strong enough to carry trains, flexible enough to survive powerful winds and earthquakes, and durable enough to remain operational for generations. Their answer was an enormous steel arch. Instead of building a bridge supported by countless columns reaching down into the Chenab River, engineers designed a giant arch that would span the valley. The concept sounds simple, the execution was anything but. The planned bridge would stretch for roughly 1.3 kilometers from one side of the mountain to the other, with its main arch spanning around 467 meters at its highest point. The railway would sit roughly 359 meters above the river. That meant engineers weren't simply building a bridge, they were essentially constructing a giant steel structure in the middle of a mountain range. And before construction could even begin, they had to understand the mountains. Survey teams studied the geology, the rock formations, the slopes, seismic conditions, wind patterns and the behavior of the river. Every detail mattered, because a mistake at ground level could become a disaster hundreds of meters above it. The mountains also created another problem. There was no easy highway leading directly to the construction site. So roads, access routes, tunnels and temporary infrastructure had to be developed simply to bring equipment and materials into position. Then came the foundations. The bridge needed two enormous concrete foundations on opposite sides of the valley. These foundations would eventually carry the forces generated by the giant arch. But drilling and excavating into Himalayan rock is nothing like digging a normal construction site. Workers had to cut into steep mountain slopes while carefully controlling excavation and stabilizing the surrounding rock. Rock bolts, anchors and reinforced concrete were used to strengthen the mountainside and create secure platforms for the bridge. Then the steel began arriving, and this wasn't ordinary structural steel. The bridge required thousands of tons of specially engineered steel components, designed to withstand the enormous forces created by trains, wind, temperature changes and earthquakes. But there was a major logistical problem. How do you transport enormous pieces of a bridge into one of the most remote mountain environments in India? Some components had to travel long distances by road before being moved through increasingly difficult terrain in several areas. Engineers couldn't simply bring massive pieces directly to the site. So the bridge had to be designed in sections that could be transported, positioned and assembled in a controlled sequence. And then came one of the most impressive parts of the entire project, the arch. Building a giant arch across a valley is fundamentally different from constructing a normal bridge. The engineers couldn't simply place the completed arch across the gap, it was far too large. Instead, the arch had to be assembled progressively from both sides. Temporary support systems and cable arrangements were used to help hold the growing steel structure in position while workers continued adding sections. Imagine two construction teams working high above a river, slowly extending enormous steel pieces toward each other. Every section had to be positioned with extraordinary precision, because as the arch grew longer, even a small error could become a serious problem. Surveying equipment continuously monitored the structure. Engineers had to account for temperature, because steel expands and contracts. They had to account for wind, they had to account for the weight of the unfinished structure, and they had to calculate how every new section would change the forces acting on everything already installed. It was essentially a giant three-dimensional puzzle being assembled hundreds of meters above the ground. Then the two sides finally moved toward each other. And in one of the most important moments of the entire project, the massive arch was connected across the valley. That connection transformed dozens of separate steel components into one enormous structural system. But the bridge still wasn't finished. The railway deck had to be built above the arch. Vertical members rise from the arch to support the railway structure, transferring the weight of the trains down into the main arch and ultimately into the foundations. The result is a bridge that looks almost impossible when viewed from the valley below, a huge steel curve stretching between two mountains, with the railway sitting high above it. But beauty was never the main objective. Safety was. The Himalayan region is seismically active, so the bridge was engineered with earthquake resistance in mind. It also had to survive extreme temperature variations. In winter, temperatures can fall dramatically, while summer conditions can produce significant expansion in the steel. The bridge therefore had to be capable of moving slightly without losing its structural integrity. Then there was the wind. At this altitude and in this terrain, wind can become a serious engineering challenge. The bridge was designed and tested to withstand powerful wind conditions. While its aerodynamic characteristics were carefully studied, even the possibility of explosions and other extreme events was considered during the engineering process, because when a railway bridge becomes this important, engineers can't simply design it for an ordinary day, they have to design it for the worst day imaginable. And perhaps one of the most fascinating things about the Chenab rail bridge is that workers had to perform all of this while dealing with the reality of the Himalayas. Weather could change quickly, snow could interrupt work, rockfalls could create danger, access routes could become difficult, and at times, construction could feel like a battle against the landscape itself. Yet the project continued piece by piece, bolt by bolt, section by section. The bridge gradually emerged from the mountains. Eventually, the enormous structure stood complete above the Chenab River. From a distance, it almost looks unreal, a giant steel arch suspended between mountains with a railway line running across the sky, but its purpose goes far beyond breaking records. The bridge forms a critical part of the Udhampur-Srinagar-Baramulla rail link, a massive railway project designed to improve connectivity between the Kashmir Valley and the rest of India's railway network. For the people living in the region, that connection could mean much more than faster transportation. It can improve access to markets, education, employment, tourism and essential services, while making travel through difficult mountain terrain easier and more reliable. And this is what makes the bridge so fascinating. It wasn't built simply because engineers wanted to create the world's highest railway bridge. It was built because geography created a problem, and engineers refused to accept that the mountains had the final word. The project also represents a remarkable combination of modern engineering and old-fashioned construction. Determination computers were used to model the structure, advanced surveying equipment helped position components, specialized steel was manufactured and transported, massive cranes and cable systems helped move components into place. But at the center of everything were thousands of workers and engineers who had to physically build the structure in one of the most difficult environments imaginable. Think about the scale for a moment. A train traveling across the finished bridge is moving hundreds of meters above the river. The passengers may simply look through the window and see mountains, but underneath them is an enormous engineering system carrying the weight of the train, distributing forces through the deck, down through the vertical supports, into the giant arch and finally into foundations anchored deep into the mountains. Every part has a job, every connection matters, and every calculation made during construction ultimately contributes to keeping that train safely in the sky. Perhaps that's the greatest lesson of the Chenab rail bridge. The bridge isn't impressive because it is tall, it is impressive because of the number of problems that had to be solved before that height became possible. The mountains had to be studied, the rock had to be stabilized, roads had to be created, steel had to be manufactured and transported, the arch had to be assembled in midair, wind, earthquakes, temperature and long-term durability had to be considered. And after years of planning, construction and testing, the impossible-looking structure finally became a railway bridge. Today, when a train crosses the Chenab River high above the Himalayan valley, the passengers may only see a few minutes of breathtaking scenery, but those few minutes represent years of engineering, planning, risk and human effort. And perhaps that is what makes this bridge more than just another piece of infrastructure. It is a reminder that some of the world's greatest engineering achievements begin with a simple question: what if we tried anyway? Because when India looked at a massive Himalayan valley and saw a barrier, its engineers saw a gap that could be crossed, and across that gap now stands one of the most extraordinary railway structures ever built, a bridge above the river, a railway above the mountains, and, for a brief moment, a piece of human engineering seemingly suspended between the earth and the sky.